The morning of February 22nd, 1943, near Spitler, Tunisia, Panzerabteilung 501's reconnaissance units picked their way through abandoned American positions, cataloguing the chaos of retreat. Among destroyed half-tracks and scattered equipment, they found something that would alter German understanding of American industrial capability. An M4A1 Sherman tank, virtually intact, engine still warm, ammunition racks partly full. The tank bore the name War Daddy II painted on its hull. Serial number USA 3067641, built by Lima Locomotive Works. This single vehicle, captured from Company G of the 1st Armoured Regiment, would spend the next year teaching German engineers lessons they desperately did not want to learn. But what German intelligence could not anticipate as they prepared this trophy for shipment to the fatherland was that American ordnance engineers were already developing an upgrade that would render their careful testing obsolete before the reports could be fully analyzed. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The decision to ship War Daddy II to Germany reflected urgent priorities within the Wehrmacht's technical branches. American tank production had been documented through intelligence reports, but seeing the physical vehicle made those statistics real in ways numbers on paper never could. The Sherman represented mass production at a scale Germany could not match, built with automotive engineering principles Germany had not mastered. As the captured tank rolled onto a cargo ship bound for Germany, Wehrmacht engineers prepared testing protocols that would reveal truths about American capabilities and uncomfortable realities about German limitations. What they could not know was that even as War Daddy II steamed northward across the Mediterranean, American ordnance engineers at Aberdeen Proving Ground were wrestling with a problem that their captured Sherman represented. The 75mm M3 gun that armed most Shermans had proven adequate against early German tanks in North Africa. But intelligence reports from the Eastern Front described new German vehicles with dramatically improved armor protection. A tank designated the Panzerkampfwagen 5, soon to be known simply as the Panther. Spring 1943 found War Daddy II at Kummersdorf Proving Ground, Brandenburg, 25 kilometers south of Berlin. The German Army's primary testing facility for both German and captured Allied equipment. Test engineers had already stenciled armor thickness measurements and angles across every surface of the tank, marking it with precise notations for comprehensive evaluation. The designation Butte Panzerkampfwagen M4738 captured American tank M4 and German license, plate WH058941. Now identified this Sherman that had crossed an ocean and changed hands through combat. German engineers photographed every component from dozens of angles, measured every clearance with precision instruments, documented construction techniques that seemed impossibly straightforward compared to German methods. The transmission caught immediate attention from powertrain specialists. Where German tanks employed straight-cut gears requiring precise tolerances and frequent maintenance, the Sherman used herringbone-cut gears that distributed stress across multiple teeth simultaneously. This design, standard in American automotive manufacturing since the 1930s, provided exceptional durability with minimal precision requirements. German engineers had considered herringbone gears too difficult to mass-produce given their industrial capabilities and workforce training. The Americans had been manufacturing them by the thousands. The testing began with basic automotive trials designed to stress every mechanical system under controlled conditions. Engineers drove War Daddy II through obstacle courses designed to replicate battlefield conditions, measuring fuel consumption, monitoring engine temperatures, recording transmission behavior under varying loads and terrain. After each trial, they disassembled components to examine wear patterns, looking for signs of stress, inadequate lubrication, design weaknesses. The results contradicted everything German tank doctrine had accepted about necessary trade-offs between performance and reliability. The Sherman performed adequately in every category and excelled in the one metric German tanks consistently failed. Operational endurance, without maintenance intervention. The Continental R975 radial engine, demonstrated remarkable tolerance for varied operating conditions. Engineers noted that the engine maintained consistent performance across temperature ranges that would have caused German engines to overheat or lose power. The cooling system, though simple in design, proved highly effective. The air filtration system handled desert sand without the frequent clogging that plagued German tanks in North Africa. Every system reflected a design philosophy that prioritized practical functionality over theoretical optimization. June 6th and 7th, 1943. Hillesleben Artillery Range. Reichsminister Albert Speer arrived to preside over a major armament conference attended by leaders from the armaments industry and senior Wehrmacht officers. The demonstration program included hill-climbing trials comparing German and captured Allied tanks. War Daddy II sat alongside the latest German designs, including a Panther Ausführung D medium tank fresh from production and a Ferdinand tank destroyer, representing Germany's most advanced armoured fighting vehicle technology. Speer, responsible for German armaments production and personally accountable to Hitler for results, needed to understand what American industry could produce and how German designs measured against enemy equipment. The Sherman climbed the test slope smoothly, its manual transmission with 5 forward gears, synchronized from 2nd through 5th, shifting without hesitation. Its engine maintaining consistent power delivery throughout the ascent. The driver handled the vehicle with confidence, demonstrating the ease of operation that would become a Sherman hallmark. The Panther followed, its more powerful 700 horsepower Maybach HL230 engine, allowing it to match the Sherman's performance, but only barely and with considerably more difficulty. The Ferdinand, massively heavy at 65 tons and technically sophisticated with its electric transmission system, stalled partway up the incline. Speer watched as recovery crews struggled to restart the vehicle, the embarrassing failure occurring before dozens of senior officers and industrial leaders. In his memoirs years later, Speer would write about Sherman capabilities he observed during his inspection tour of Italy in October 1944. He noted that reports on the cross-country mobility of the Sherman had been very favourable, with the tank climbing mountains German tank experts considered inaccessible to tanks. He attributed this to the Sherman having a very powerful motor in proportion to its weight, giving it cross-country mobility on level ground that was definitely superior to German tanks. The written public assessment appeared in Das Reich newspaper on June 27, 1943. The article described the Sherman as one of the special accomplishments of the North American laboratories and called it quite a praiseworthy product of the North American steel industry. The article noted that the first things to attract attention were serial construction and fulfillment of the almost arrogant requirements of the North American automobile industry. These public statements, carefully worded for propaganda purposes to avoid appearing defeatist, nevertheless concealed the private alarms spreading through German engineering departments. American tanks weren't just adequate, they were fundamentally better engineered for sustained field operations. But what troubled German analysts most as they compiled their reports through summer and autumn 1943 was not what the Sherman could do. It was what the Sherman represented. American automotive engineering maturity that Germany fundamentally lacked despite its theoretical knowledge and scientific expertise. Back at Kummersdorf, systematic testing continued. Engineers measured the Sherman's operational range, conducting extended trials that pushed the vehicle to its limits. They documented operational ranges exceeding 2,000 kilometers before requiring major maintenance, roughly 4 times what early model Panthers could achieve in field conditions. They measured transmission efficiency that exceeded any German tank, with power losses through the drivetrain significantly lower than comparable German systems. They examined the synchronized manual transmission that made gear changing smooth and simple, requiring neither the double clutching nor the careful rev matching that German transmissions demanded. By late 1943, Kummersdorf had accumulated enough data to produce comprehensive internal reports that circulated through Wehrmacht technical branches. These documents, intended for senior Wehrmacht officers and armaments ministry officials, painted a sobering picture of comparative capabilities. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked. Mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing, yet resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training, while German vehicles required factory-level precision and specialized equipment for many repairs. The entire design philosophy prioritized keeping vehicles operational rather than achieving theoretical performance maximums that looked impressive in specifications but couldn't be maintained in combat. But the Sherman that German engineers tested so meticulously at Kummersdorf carried a 75mm gun. And even as German analysts compiled their reports praising American automotive engineering, they drew comfort from one inescapable conclusion. The Sherman's firepower was inadequate against the newest German tanks. The 75mm M3 gun could not penetrate a Panther's frontal armor at any range. The round would simply bounce off the sloped glacis plate. This firepower deficiency appeared in every German technical assessment. The Sherman was an excellent vehicle platform, mechanically superior to German designs in reliability and maintainability, but it lacked the gun to pose a serious threat to Panthers or Tigers when engaged frontally. German tank doctrine could adjust to face an enemy with superior numbers and better logistics. Crew training emphasized exploiting the Panther's armor and firepower advantages to defeat Shermans at ranges where American guns were ineffective. What German intelligence failed to anticipate as they filed their Kummersdorf reports through late 1943 and early 1944 was that American ordnance engineers were not satisfied with the 75mm gun either. Testing and development of a more powerful weapon had begun in July 1942, even before the Sherman entered widespread combat. The 76mm gun M1 represented a fundamental departure in American tank armament philosophy. The development history of the 76mm gun revealed bureaucratic, hesitation, and technical challenges that nearly prevented its deployment entirely. The United States Army had recognized the need for improved anti-tank capability, but doctrine stated that the role of a tank was infantry support, not fighting other tanks. Armored Forces Field Manual Tactics and Techniques listed tank versus tank combat as special operations, with less than a page devoted to the subject. The 75mm gun was retained for use in tanks because of the performance of its high explosive shell. The M61 75mm armor-piercing capped round was the anti-tank armament used in United States medium tanks, despite its inability to defeat the frontal armor of even the Panzer IV when that German tank received improved armor. The United States Army got its first detailed look at the Panther tank in early 1943 after Soviet forces captured examples on the Eastern Front and shared intelligence. The improvements were noted, but the Panther was not considered a tremendous threat since there were not great numbers produced at the time. This assessment would prove catastrophically wrong. American ordnance engineers had been testing the 76mm gun on Sherman hulls since early 1943. The weapon showed promise, but the existing M4 turret proved too small to accommodate the extra length. The turret from the aborted T-23 tank project was adapted and suitably modified. Despite the weapon being ready, Army ground forces rejected deployment as unnecessary. Commanders believed the 75mm gun would prove adequate for expected opposition. The first production 76mm Shermans rolled off assembly lines in January 1944. These M4A 176 Shermans arrived in Britain on April 10, 1944, with 130 tanks delivered to prepare for the Normandy invasion. Yet despite their availability, American commanders refused to deploy these improved tanks on D-Day. The reasons were multiple. Crews lacked adequate training time on the new weapon system. Logistical concerns about maintaining two different ammunition types complicated supply planning. Most critically, commanders believed the 75mm gun would prove adequate for the expected opposition. This decision, made in good faith based on available intelligence, would prove to be a catastrophic miscalculation. June 6, 1944. Operation Overlord. Allied forces landed on the beaches of Normandy with no 76mm Sherman tanks in the assault waves. The American armored force that pushed inland from the beaches was equipped entirely with 75mm guns. Within days, these units encountered something American intelligence had failed to accurately predict: Panthers in numbers far exceeding expectations. Not the handful of specialized heavy tanks intelligence had suggested, but 38% of German tanks in Normandy, hundreds of Panthers, many crewed by inexperienced soldiers, but protected by armor that conventional American tank guns could not penetrate frontally. The tactical reality became clear quickly and painfully. A Sherman with a 75mm gun could not engage a Panther frontally at any range. The German tank could destroy Shermans from 2,000 meters away, while remaining effectively invulnerable to return fire. By early July 1944, field reports from Normandy painted a grim picture. Tank crews who had trained confidently, believing in American technological superiority, found themselves outgunned by an enemy they could not hurt from the front. On July 2nd, complaints about the 75mm gun's ineffectiveness against German armor reached General Dwight Eisenhower. His response, documented in multiple historical accounts, captured command-level frustration. "You mean our 76 won't knock these Panthers out? Why, I thought it was going to be the wonder gun of the war." The full quote, as recorded by witnesses, continued with stronger language, expressing his anger that ordnance had assured him the 76mm would take care of anything the Germans had. A board convened on July 12, 1944, determined officially what tank crews already knew from bitter experience. Standard American weapons could not defeat Panthers frontally. General Omar Bradley immediately ordered the 76mm Shermans rushed from Britain to the front. On July 25, 1944, during Operation Cobra, 102 M4A, 176 tanks made their combat debut. The operation marked the beginning of the breakout from Normandy, with American armored divisions pushing through German defenses that had held the Bocage country for weeks. The 76mm Shermans performed adequately, providing improved anti-tank capability that crews had desperately needed. But the initial engagement reports revealed a sobering truth. While the 76mm represented an improvement over the 75mm, it still struggled against Panther frontal armor at combat ranges. Sherman crews quickly learned they needed to maneuver for flank shots or target the Panther's gun mantlet at close range, typically under 100 meters. Neither option being tactically desirable when facing a tank that could destroy them from 2,000 meters away. The comparison between what German engineers had tested at Kummersdorf and what American tankers now faced in Normandy's hedgerows revealed the fundamental miscalculation. German analysts had correctly identified the 75mm Sherman's firepower limitations. Their reports emphasized this weakness while acknowledging American automotive superiority. But those reports were written about a tank that was already becoming obsolete, even as German engineers compiled their findings. The 76mm gun existed, it was in production, it was being shipped to Europe, and it represented a capability that German intelligence had failed to incorporate into their tactical assessments. Even the improved 76mm gun, however, struggled against Panther frontal armor when firing standard ammunition. The M62 armor-piercing capped rounds could penetrate 109 millimeters of armor at 1,000 meters at 0 degrees obliquity. This was sufficient against the Panzer IV and many German assault guns, but the Panther's sloped frontal armor remained effectively immune, except at extremely close range. American ordnance engineers recognized this limitation even before the first 76mm Shermans entered combat. The solution lay in metallurgy and physics. By July 1944, American ordnance had developed the T4 round, later standardized as the M93 HVAP. High-velocity armor-piercing ammunition represented a fundamental departure from conventional armor-piercing design. The projectile consisted of a tungsten carbide core, one of the hardest materials available, surrounded by a lightweight aluminum body and ballistic windshield. This design concentrated the projectile's kinetic energy into a smaller, denser penetrator while reducing overall weight. The result was dramatic. The M93 round achieved a muzzle velocity of 1,036 meters per second compared to 792 meters per second for the standard M62 round. This 244 meter per second velocity increase translated directly into penetrating power. At 1,000 yards, approximately 914 meters, the HVAP round could penetrate 160 millimeters of armor at 10 degrees obliquity. According to official War Department testing data, this meant reliable penetration of the Panther's gun mantlet at ranges up to 1,000 meters instead of point-blank distance. The mantlet suddenly became a viable target for Sherman crews who had previously been forced to attempt desperate flank attacks or retreat. But the development of HVAP represented only half the solution. Production was another matter entirely. The T4 round depended on tungsten carbide, a strategic material imported primarily from China, which produced 36% of global tungsten supply before the war. Tungsten was critical to numerous war industries. Machine tools, armor-piercing ammunition for multiple calibers, armor plate hardening, and various industrial processes all competed for limited supplies. American tungsten demand for HVAP ammunition alone consumed hundreds of metric tons annually. Each 76mm HVAP round contained approximately 0.88 kilograms of tungsten carbide, meaning a Sherman carrying 6 rounds required nearly 5 kilograms of this scarce material. China produced approximately 10,000 metric tons of tungsten concentrates in 1944, but this had to serve all Allied needs across all applications. The United States supplemented Chinese imports with domestic production from limited deposits in Colorado, Nevada, and California, but total availability remained constrained. The United States Ordnance Department had been testing HVAP projectiles since spring 1942, but production at scale did not begin until after the Normandy landings revealed the extent of the Panther problem. In July 1944, production of 3-inch HVAP rounds for tank destroyers reached 1,000 rounds. August saw 1,000 rounds of 76mm HVAP produced. September yielded another 1,076mm rounds. Not until November 1944 did monthly production reach 5,000 rounds for the 76mm, ramping to 7,000 rounds per month by January 1945. By March 1945, approximately 33,000 rounds of 76mm HVAP ammunition had been produced, representing a significant industrial effort, but still a fraction of what was needed. By February 1945, the average 76mm Sherman in Europe had received a total of 5 HVAP rounds. 5 rounds to face an enemy, deploying Panthers as the standard tank in Panzer divisions. A Sherman company with 17 tanks would possess 85 HVAP rounds total while facing German units that might field 30 or more Panthers. The first HVAP rounds reached the European theatre in August 1944, but their arrival was overshadowed by broader tactical problems and the limited quantities available for distribution. The ammunition arrived at a time when American ordnance personnel needed to conduct formal testing to establish capabilities and limitations. France, August 1944. Testing. Facilities near Isigny. American ordnance officers had assembled captured German tanks for comprehensive firing trials. 3 Panther tanks, captured during the Normandy campaign, sat in the proving ground that Allied engineers had established in recently liberated territory. The tests conducted at Isigny between July 12 and August 21, 1944, would provide the first systematic American data on how various weapons performed against actual Panther armor under controlled conditions. The results would profoundly influence American tactical doctrine and ammunition priorities for the remainder of the war. The board convened on July 19 at the firing range established by 1st United States Army near Isigny, conducted tests against all available anti-armor weapons. The 75mm gun was tested, the 3-inch gun on the M10 tank destroyer, the new 76mm gun, and, for comparison, the British 17-pounder. The reports, issued after 2 sets of firing tests at Isigny, painted a bleak picture of the capabilities of the Sherman's existing 75mm gun, as well as the new 76mm, which was being used in upgunned models. The tests showed that the 75mm gun could not penetrate a Panther's front from any range. The 76mm, using its main armor-piercing round, could not penetrate the front of the hull at any range, but could penetrate the mantlet at about 200 yards or less. The rounding of the mantlet played into the issue. Striking the top quarter of the mantlet could well lead a projectile to ricochet off into the sky. Crews needed to hit the mid-half to penetrate the turret, or the lower quarter to have a chance of ricocheting into the hull roof. The ammunition that would change this tactical calculus arrived by air in August. 1,000 rounds of the new T4 HVAP ammunition for both the 76mm gun and the 3-inch gun. Priority was given to testing this new ammunition to determine if it could solve the Panther problem. The second set of tests conducted at Isigny were organized under order of the 12th United States Army Group. The testing board convened on August 19th at the same firing range. These tests were specifically against Panthers and were to compare the United States 76mm gun and new HVAP ammunition to the British 17-pounder. The board fired 76mm HVAP projectiles, 17-pounder armor-piercing capped ballistic cap rounds, and 17-pounder armor-piercing discarding sabot rounds at the front plate of 3 Panther tanks. The firing was continued, as weather and availability of target tanks permitted, on August 20th and 21st. The results provided both hope and sobering realism about American anti-tank capabilities. The 17-pounder armor-piercing capped ballistic cap and the 76mm HVAP were both highly accurate ammunitions. In the opinion of board members with considerable test firing experience, the 76mm HVAP was the most accurate tank or anti-tank ammunition encountered to date. The 17-pounder armor-piercing capped ballistic cap was judged more effective against the front of a Panther tank than the 76mm HVAP, but its margin of superiority was not great. Neither one could be depended upon to penetrate the glacis plate in one fair hit on average quality plate. Wide variation was found in the quality of glacis plate on the 3 tanks tested. One tank, referred to as the best plate, sustained 30 hits at ranges from 600 to 200 yards without cracking. The other 2 tanks, with average plate, cracked after relatively few hits. Against the Panther's gun mantlet, both the 17-pounder and 76mm HVAP achieved penetrations at combat ranges. The mantlet, with its curved 100mm thick cast steel on early models, became vulnerable to American fire at ranges that allowed Sherman crews to engage with reasonable expectation of achieving kills. The Isigny tests validated what American ordnance engineers had hoped. HVAP ammunition transformed the 76mm Sherman from a tank that could only hurt Panthers at suicidal close range into a vehicle that could engage enemy armor at 1,000 meters when targeting the mantlet. This represented a genuine tactical revolution. But the tests also revealed limitations that would constrain HVAP effectiveness throughout the war. The tungsten carbide core, while excellent at penetrating armor when conditions were favorable, was inherently brittle. Below certain impact velocities, approximately 2,300 to 2,500 feet per second, the core could shatter on contact rather than penetrating. This meant that HVAP effectiveness declined significantly at longer ranges where velocity had decreased. Beyond approximately 1,000 meters against Panther mantlets, the probability of the core shattering on impact increased substantially. The Isigny tests provided ammunition that American tankers needed, but could not adequately supply. Production constraints meant HVAP would never be available in the quantities required. Tank destroyer units, whose mission focused specifically on anti-tank combat, received preferential allocation. Sherman tanks, with their dual role of supporting infantry and engaging armor, often received fewer rounds despite encountering enemy tanks more frequently. This created operational tension between tactical needs and supply realities. As 76mm Shermans reached frontline units through autumn 1944, they carried perhaps 5 or 6 HVAP rounds per tank. Crews were briefed on the ammunition's capabilities and limitations. Use them wisely, commanders emphasized, against Panther turrets or mantlets at ranges where velocity remained sufficient for penetration. The psychological impact of possessing this ammunition proved as important as its actual use. Crews that knew they had weapons capable of defeating Panthers approached engagements with more confidence than those who felt helpless against German heavy armor. The knowledge that HVAP ammunition existed, even in limited quantities, fundamentally altered American tactical psychology in ways that German intelligence struggled to comprehend. Sherman crews who had fought through Normandy's hedgerows with growing apprehension about facing Panthers now possessed a weapon that offered reasonable chances of achieving penetration under favorable circumstances. This psychological shift had direct tactical consequences. Confident crews fought more aggressively, took calculated risks when opportunities appeared, and exploited tactical advantages rather than retreating when Panthers were spotted. Even crews that had never fired an HVAP round benefited from, knowing the ammunition existed and might be available when most needed. German intelligence officers examining destroyed Panthers in autumn 1944 found evidence that troubled them deeply. Entry holes smaller than expected, suggesting a sub-caliber projectile. Examination of unexploded rounds recovered near disabled tanks revealed the truth. The Americans had deployed tungsten core ammunition. This discovery had profound strategic implications. Germany itself had developed similar ammunition, the Panzerkampfwagen 40, which used tungsten cores to improve penetration. But German tungsten supplies were critically limited by late 1944, with production focused on machine tools rather than ammunition. If Americans could field specialized tungsten core ammunition in quantities sufficient to distribute to frontline tank units, it demonstrated industrial capacity and resource access that Germany could not match. Not only were American tanks more numerous and better, supported logistically, but they were now equipped with ammunition that partially negated Germany's carefully engineered technical advantages in armor protection. The impact extended beyond immediate tactical results. As word spread through American armored units that the new ammunition could defeat Panthers under favorable circumstances, tank crews became more willing to engage German armor directly. The psychological paralysis that had affected some units during the difficult Normandy fighting began to dissipate. Crews still respected the Panther's capabilities, but no longer felt helpless against it. German tank commanders began reporting to headquarters that American Shermans possessed new, more powerful ammunition. The reports were confused and contradictory. Some claimed the Americans had secretly deployed tank destroyers with 90mm guns. Others suggested the British had provided 17-pounder Firefly tanks to American units. The truth, that American industry had developed specialized ammunition that partially negated the Panther's armor advantage, was more troubling to German planners than any of these theories. It meant that American industrial capacity could respond to tactical problems faster than German industry could counter them. September 1944 found Lieutenant General George Patton's Third Army deep in France, racing toward the German border with logistics stretched to breaking point. The 4th Armored Division, one of the most effective American armored formations, had advanced aggressively, seizing a bridgehead over the Moselle River near Araucourt. German High Command recognized the threat. If Patton's armor reached the Rhine and crossed into Germany proper, the industrial heart of the Reich would be exposed. General Hasso von Manteuffel's 5th Panzer Army received orders to counterattack, destroy the American bridgehead, and push back Patton's advance. The German force assembled for this attack included 2 newly formed panzer brigades, the 111th and 113th, equipped primarily with Panther tanks fresh from German factories. On paper, the German advantage appeared overwhelming. The 2 brigades together fielded approximately 150 tanks against Combat Command A of the 4th Armored Division, which possessed roughly 50 Sherman tanks. The 113th Panzer Brigade alone entered battle with approximately 90 tanks and assault guns in both battalions combined, including 42 Panthers and 40 Panzer IVs. German planners anticipated a rapid victory. The Panther's technical superiority should compensate for any American advantages in logistics or air support. They were fundamentally mistaken. The Battle of Aracourt, fought over 11 days from September 18th to 29th, would become the largest tank engagement fought by American forces until the Battle of the Bulge. More importantly, it would demonstrate that American tank crews, properly trained and equipped, could defeat technically superior German armor through superior tactics, combined arms coordination, and judicious use of high-velocity armor-piercing ammunition. The morning of September 19th began with thick fog blanketing the rolling terrain around Aracourt. German reconnaissance was limited. The Panzer brigades, lacking proper scouting units, advanced blindly into terrain held by American forces who knew the ground and had established defensive positions. At approximately 8 o'clock in the morning, elements of the 113th Panzer Brigade penetrated American outposts east and south of Aracourt. The German tanks, factory-new Panthers with inexperienced crews, moved forward in column formation, a tactical error that veteran American tankers immediately exploited. Captain Kenneth R. Lameson's C Company, 37th Tank Battalion, held positions along key approaches to Aracourt. His Sherman crews had been briefed on the HVAP rounds in their ammunition racks. 6 rounds per tank. Use them wisely, the briefing had emphasized, against Panther turrets or mantlets at ranges where velocity remained sufficient for penetration. The fog that hindered German reconnaissance now worked in favor of American defenders. A section of Lameson's Shermans occupied positions south of the village when the first Panther materialized from the mist, barely 75 meters away. At this range, the Panther's superior long-range gunnery meant nothing. The American gunner fired instantly. The HVAP round, traveling at over 1,000 meters per second, struck the Panther's gun mantlet. The tungsten carbide core punched through the curved cast steel and detonated the ammunition stored directly beneath the gun breech. The Panther exploded, its turret lifting slightly from the force of the secondary detonation. 2 more Panthers emerged from the fog in quick succession. Both were destroyed within seconds, their crews having no time to effectively return fire in the limited visibility. The remaining German tanks turned away, crews shocked by the sudden loss of 3 Panthers to what they had been told were inferior American tanks. Throughout the morning of September 19th, similar engagements erupted across the Aracourt sector. American tanks using the fog as concealment engaged Panthers at ranges where HVAP rounds were most effective. The German tactical deployment proved disastrous. Advancing in column without proper reconnaissance, Panther crews repeatedly exposed their thinner side armor to American flanking fire. Near Aracourt's command post, a platoon of M18 Hellcat tank destroyers, also equipped with 76mm guns and HVAP ammunition, engaged German armor at close range. The fast-moving tank destroyers proved devastatingly effective in the close-range fog-shrouded combat. By noon, as the fog lifted, American forward artillery observers could coordinate fire with defending tank companies. P-47 Thunderbolt fighter bombers of the 405th Fighter Group arrived overhead, diving through gaps in the cloud to strike German armor with rockets and machine guns. The combination of American advantages became clear. While the Panther possessed superior armor and firepower as an individual weapon system, American forces employed combined arms tactics as standard doctrine. German tanks advanced without adequate artillery support, without air cover, without infantry to clear American defensive positions. American forces coordinated armor with artillery, air power, infantry, and tank destroyers in an integrated system that overwhelmed German technical advantages. When Panthers encountered these prepared defenses, they were destroyed piecemeal despite their superior capabilities. The HVAP ammunition did not make Sherman tanks equal to Panthers in technical specifications, but warfare is not conducted according to technical specifications alone. Tanks are destroyed by crews who exploit vulnerabilities under combat conditions. The Panther's gun mantlet, necessary to allow the 75mm gun to elevate and traverse, created a weak point. The junction between turret and hull, the side armor, the engine deck, all represented targets that HVAP-equipped Shermans could now engage successfully at combat ranges that previously had been suicidal. More devastating to German morale was the psychological impact of discovering their armor was no longer invulnerable. Panther crews had been trained to believe their tanks could not be penetrated frontally by American fire. Intelligence briefings emphasized the Shermans' inadequate firepower. Crews were told that as long as they kept the front toward the enemy, they were safe. The first Panther commanders to watch Sherman rounds punch through their mantlets and detonate ready ammunition learned otherwise. Survivors of such encounters carried that knowledge back to their units, spreading awareness that American tanks now possessed ammunition capable of defeating Panthers. By the afternoon of September 19th, German tank commanders were reporting to headquarters that American Shermans possessed new, more powerful ammunition. The fighting continued through September 22nd, when the major German offensive efforts finally stalled. American forces had destroyed or disabled approximately 86 German tanks and assault guns. American losses stood at 25 Sherman tanks and 7 tank destroyers. The kill ratio heavily favored the Americans despite their technical disadvantage in individual tank performance. The Battle of Aracourt represented not just a tactical victory, but a psychological watershed. American tank crews learned that they could defeat Panthers without waiting for specialized tank destroyers or overwhelming air support. German crews lost the psychological security of believing in absolute frontal invulnerability. The German perspective on Aracourt was one of confusion and bitter recrimination. The 113th Panzer Brigade, which had entered battle with approximately 90 tanks and assault guns, could muster fewer than 20 operational vehicles by September 29th. German after-action reports struggled to explain the defeat. The technical superiority of the Panther was undeniable on paper. How had inexperienced crews in newly produced tanks been defeated so comprehensively? The answers lay partly in training and experience. The Panzer Brigade crews had minimal training, often arriving at the front with only weeks of instruction. American tank crews in the 4th Armored Division were veterans who had fought across France, understood combined arms warfare, and had learned to read terrain for tactical advantage. But training alone did not fully explain Panther losses, particularly the penetrations that should not have been possible with standard American ammunition. German intelligence officers examining destroyed Panthers found clear evidence of HVAP penetrations. The smaller entry holes, the characteristic damage patterns, all pointed to sub-caliber tungsten core projectiles. German engineers understood the principles. They had developed similar ammunition themselves. What troubled them was the implication that Americans could produce such ammunition in quantities sufficient to distribute to frontline Sherman crews. This demonstrated industrial depth that Germany could no longer match. As autumn 1944 progressed into winter, American 76mm Shermans became increasingly common in frontline units. By December, when German forces launched their surprise offensive in the Ardennes, American tank units faced renewed intense pressure. The Battle of the Bulge saw hundreds of Panthers and Tiger tanks deployed in winter conditions that favored defensive fighting and limited Allied air superiority due to poor weather. American Sherman crews relied heavily on their scarce HVAP ammunition to engage German heavy armor. The shortage became critical within days of heavy fighting. Some units exhausted their HVAP supply completely and found resupply requests going unfulfilled as logistical networks struggled to deliver ammunition through snow-blocked roads disrupted by German advances. Yet even in the difficult fighting of the Ardennes, American forces demonstrated that tactical skill and combined arms coordination could compensate for technical disadvantage. Tank crews coordinated closely with infantry, using bazooka teams to disable Panthers from close range, while Shermans provided covering fire. Artillery forward observers called in time on target missions that damaged optics, disabled tracks, and killed exposed crew members, even when shells could not penetrate armor. Air support, when weather finally permitted in late December and January, proved devastatingly effective against German armor concentrated on approach roads. The Battle of the Bulge ended with German armored forces shattered, having lost hundreds of irreplaceable tanks and experienced crews in an offensive that failed to reach its objectives. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By early 1945, the strategic picture had shifted decisively and irreversibly in Allied favor. American and British forces were preparing to cross the Rhine. Soviet armies were advancing from the east, having shattered German defensive lines in massive winter offensives. Germany's industrial capacity was collapsing under combined strategic bombing, loss of territory containing critical resources and manufacturing facilities, and severe shortages of raw materials including fuel and tungsten. Panther production, which had reached 3,900 units in 1944, fell sharply in early 1945 as factories were bombed, transportation networks disrupted, and raw materials became unavailable. Even when Panthers were produced, fuel shortages often kept them immobile. German tank units in the final months frequently abandoned tanks not because of combat damage, but because they had no fuel to operate them. What German engineers at Kummersdorf had never anticipated as they tested War Daddy II through 1943 was that American industrial capacity would not simply produce more of the same vehicle. American ordnance engineers had identified the Sherman's firepower limitations even before German analysts compiled their reports. The 76mm gun development had begun in July 1942, months before War Daddy II was even captured. The HVAP ammunition development followed naturally from American experience with armor-piercing projectile design dating back to the 1930s. German engineers, testing the 75mm Sherman at Kummersdorf, had drawn accurate conclusions about that specific vehicle's capabilities and limitations. Their error was assuming American industry would remain static, continuing to produce the same design without improvement. This fundamental misunderstanding of American industrial philosophy would characterize German intelligence failures throughout the war. American automotive engineers approached tank design with principles learned from decades of civilian vehicle production. Design for continuous improvement. Build in margins for future upgrades. Prioritize reliability and maintainability over theoretical performance peaks. The Sherman's large turret ring, which German engineers had noted during Kummersdorf testing, was not accidental. It provided growth potential that allowed mounting significantly larger guns without complete vehicle redesign. The British Firefly, mounting the 17-pounder gun in a Sherman turret, demonstrated this adaptability. American 76mm Shermans followed the same principle. The basic hull and suspension designed for a 30-ton vehicle with a 75mm gun could accommodate a 42-ton assault tank with dramatically increased armor protection. German tank design philosophy worked differently. Panthers were designed to specific performance requirements with minimal margins for growth or modification. The Maybach engine was already overtaxed, supporting the 45-ton vehicle. The transmission and final drives operated at their design limits. Adding additional armor or a larger gun would require complete redesign of the powertrain. This design philosophy meant Panthers could not be significantly upgraded without factory-level modifications. When German engineers recognized the need for improvements, they had to halt production lines, retool equipment, and train workers on new procedures. American production lines built continuous improvement into their processes. Sherman, variants with different engines, different hulls, different armaments rolled off parallel production lines with fully interchangeable components wherever possible. A crew could transition from one Sherman variant to another with minimal retraining. Mechanics could maintain mixed fleets using common tools and shared expertise. This production flexibility, which German industry never matched during the war, meant American armor constantly improved while German designs stagnated or suffered quality degradation as production conditions worsened. The technical limitations of HVAP ammunition, while less publicized than its successes, deserve examination for historical completeness. The tungsten carbide core, while excellent at penetrating armor when conditions were favorable, was inherently brittle. Below certain impact velocities, the core could shatter on contact rather than penetrating. This meant that HVAP effectiveness declined significantly at longer ranges where velocity had decreased. The effective range against Panther mantlets was approximately 1,000 meters. Beyond this distance, the probability of the core shattering on impact increased substantially. American tankers learned these limitations through combat experience, sometimes tragically. Crews that fired HVAP at Panthers beyond effective range wasted scarce ammunition and often provoked return fire from German guns that remained effective at much longer ranges. Training on proper HVAP employment was often minimal, as the ammunition arrived at frontline units faster than training materials could be developed. Many crews learned effective employment techniques through trial and error under combat conditions. Sergeant Francis Baker's documented experience on November 20, 1944, illustrated both the potential and limitations of HVAP in actual combat. His Sherman, equipped with a 76mm gun and carrying HVAP rounds, engaged a Panther at approximately 800 yards. Baker's gunner fired at least 7 rounds with multiple hits observed on the Panther's side armor. To Baker's frustration, the rounds bounced off without achieving penetration. The engagement demonstrated that even HVAP had significant limits against sloped armor at oblique angles. The Panther withdrew from the engagement rather than continuing the fight, so the action was not a complete tactical failure. But it reminded Sherman crews that HVAP was not a magical solution. Proper tactics, careful shot placement, favorable range estimation, and advantageous angles of engagement remained critical factors. HVAP gave American tankers significantly better odds, but success still required skill and judgment. The post-war analysis of HVAP ammunition revealed both its successes and limitations. Against the Panther's gun mantlet at ranges up to 1,000 meters, HVAP was highly effective when hits were achieved, reliably penetrating and often causing catastrophic secondary explosions. Against the glacis plate, results were poor, except at very close ranges and favorable angles. The extreme slope meant that tungsten core rounds, traveling at high velocity, often ricocheted or shattered on impact. This meant Sherman crews still needed to maneuver for advantageous shot angles, flanking Panthers when tactically possible. The ammunition did not make Sherman tanks technical equals to Panthers, but it gave American crews a fighting chance in engagements where previously they had little hope of frontal penetration. The Korean War, beginning in June 1950, provided another combat test of HVAP effectiveness. American Sherman tanks, now primarily the M4A3E8 variant, armed with 76mm guns, faced Soviet-built T-34-85 tanks in North Korean and later Chinese service. Unlike the situation in Europe, where HVAP had been critically scarce, by 1950 tungsten supplies were no longer constrained by competing. Wartime demands and substantial stocks were readily available. American tank crews in Korea found that HVAP rounds easily penetrated T-34-85 armor at normal combat ranges. The T-34-85, while capable, possessed armor protection significantly inferior to the Panther. Its 90mm thick turret front and 45mm thick glacis plate could not resist tungsten core projectiles fired at high velocity from 76mm guns. American Shermans in Korea achieved remarkably favorable exchange ratios against communist armor due partly to superior crew training, but also significantly to the plentiful availability of HVAP ammunition. The vindication of the 76mm Sherman in Korea was bittersweet for veterans of European combat. The ammunition that could have been more widely employed in Europe proved devastatingly effective in Asia, when supply constraints no longer limited employment. The German perspective on American HVAP ammunition, gathered from post-war interrogations and examination of captured documents, revealed grudging professional respect and deep frustration. German ordnance officers recognized that American industry had solved the tungsten core ammunition problem more successfully than German manufacturers. Despite Germany having pioneered the underlying technology, while Germany had developed tungsten core ammunition with the Panzerkampfwagen 40 series, production limitations meant these rounds were never available in sufficient quantities. American production of HVAP, though also limited by tungsten scarcity, still exceeded German capability substantially by late 1944. German tank crews interviewed after the war frequently mentioned American ammunition improvements as a significant factor that complicated their tactical situation. The knowledge that Sherman tanks could penetrate Panther mantlets at combat ranges meant German crews could not simply rely on frontal armor for protection. This forced more cautious tactics, slower advances, and greater reliance on defensive positions. But defensive warfare ceded initiative to American forces, allowing them to employ combined arms tactics that negated German advantages. The psychological impact of losing armor invulnerability contributed to the increasingly defensive mindset that characterized German armored operations in 1945. Technical analysis of HVAP projectiles recovered from German tank wrecks provided German engineers with detailed understanding of American ammunition design. The tungsten carbide core, surrounded by lightweight aluminum body sections, represented efficient use of scarce strategic materials that maximized penetrating power while minimizing tungsten consumption per round. The lightweight carrier body allowed higher velocities without excessive barrel wear, while the dense tungsten core retained kinetic energy over distance far better than steel penetrators. German engineers recognized these advantages, but lacked the industrial capacity and material resources to respond with similar developments. By late 1944, German tank and ammunition production focused entirely on maintaining output of existing designs rather than developing new ammunition types. The Panther's Quebelke 42 75mm gun already possessed excellent penetrating power with standard ammunition against Allied tanks, so developing improved German rounds was not the critical priority. Developing new ammunition would require tungsten Germany could not spare, and retooling that factories struggling under air attack could not accommodate. German tanks in the final year fought with ammunition designs dating to 1942 and 1943, while American ammunition continued improving. The Battle of Arcourt's historical significance extended far beyond immediate tactical results. The engagement proved conclusively that American armored doctrine emphasizing mobility, combined arms coordination, superior logistics, and overwhelming material support could consistently defeat German tactical methods relying heavily on superior individual tank performance. German commanders had designed their 1944 Panzer brigades around the Panther's technical capabilities, assuming armor and firepower would compensate for inexperienced crews and limited support. This assumption proved catastrophically false. The lesson was clear to military observers on both sides. Technical excellence in weapons design mattered and provided advantages, but operational excellence in combined arms warfare, superior logistics, and better training mattered more for achieving tactical and operational success. The impact of HVAP on individual tank crews deserves consideration beyond purely technical analysis. For American tankers who had faced Panthers with only standard ammunition during difficult Normandy fighting, the arrival of HVAP represented tangible hope. The ammunition did not eliminate the Panther threat, but provided a tool that offered reasonable chances of achieving penetration under favorable circumstances. This psychological boost contributed to improved performance and more aggressive tactics. For German tankers, the knowledge that American tanks now posed a credible frontal threat fundamentally altered tactical calculations. Otto Carius, a highly decorated German tank ace who commanded Tiger tanks and survived the war, wrote extensively in his post-war memoirs about the psychological impact of facing enemies who could penetrate his armor. The sense of invulnerability that thick armor provided was crucial to crew morale and aggressive tactics. When that sense eroded, crew performance suffered measurably. Panther crews facing HVAP-equipped Shermans experienced this erosion of confidence. The mantlet became a known vulnerability that competent American crews could exploit. This knowledge made Panther crews demonstrably more cautious, slower to engage, and generally less willing to take tactical risks. The strategic implications of HVAP development extend to broader questions about technological competition in modern warfare and the crucial importance of industrial capacity. Both American and German research establishments possessed competent engineers and sophisticated understanding of ballistics and armor penetration. Both recognized the value of tungsten core ammunition early in the war, and both developed functional designs. The critical difference came down to industrial capacity and resource availability, rather than scientific knowledge. American industry could produce HVAP in quantities sufficient to influence battlefield outcomes meaningfully, though never enough to fully equip all units. German industry could barely produce enough to conduct testing. This pattern repeated across numerous weapon systems throughout the war. Germany developed sophisticated and often technically superior weapons, but could not produce them in quantities that affected strategic outcomes. American industrial capacity produced less sophisticated but highly effective equipment in overwhelming numbers. The M4 Sherman was objectively not the best tank of World War II by most technical measures, but American factories produced approximately 49,324 of them, compared to approximately 6,132 Panthers. This 8-to-1 production ratio, combined with ammunition improvements like HVAP that reduced the technical gap, proved strategically decisive. The post-war careers of veterans who fought at Aracourt reflect the enduring impact of these combat experiences on military thinking. Lieutenant Colonel Creighton Abrams, who commanded the 37th Tank Battalion at Aracourt with distinction, rose to become United States Army Chief of Staff and gave his name to the M1 Abrams main battle tank. The lessons Abrams learned about combined arms warfare, the critical importance of crew training, and the necessity of adequate ammunition influenced his entire career and the doctrine he helped develop. The M1 Abrams was deliberately designed with a powerful 120mm smoothbore gun and sophisticated ammunition types, including depleted uranium penetrators that serve functionally the same role HVAP served in World War II. German veterans of Panther units who survived the war and later joined the West German Bundeswehr brought different but equally important lessons. They had personally experienced the limitations of possessing technological superiority without the industrial base and logistics to support it. Bundeswehr armor doctrine during the Cold War emphasized quality and training, while explicitly recognizing that West Germany could not match Soviet numerical superiority. But Bundeswehr planners, informed by wartime experience, also emphasized ammunition effectiveness. The Leopard 1 and later Leopard 2 main battle tanks used sophisticated ammunition designs, informed by the realization that ammunition technology and crew training mattered as much as armor thickness. The conclusion of World War II in Europe, marked by Germany's unconditional surrender on May 8, 1945, ended the immediate tactical need for HVAP ammunition against Panthers. American ordnance officers systematically examining destroyed vehicles found clear evidence of HVAP penetrations on some wrecks, confirming the ammunition's effectiveness under favorable conditions, while noting its limitations. Panthers hit by HVAP typically showed penetrations through the mantlet or turret face when struck at favorable angles, but rarely through the glacis plate, which remained highly resistant. This pattern validated American tactical doctrine that emphasized flanking maneuvers and creating favorable engagement angles. The comprehensive post-war analysis concluded that while HVAP meaningfully improved Sherman capabilities against heavy German armor, the truly decisive factors remained overwhelming numerical superiority, vastly better logistics, complete air superiority, superior artillery support, and more effective operational doctrine. The transformation of American tank crews from mid-1944 to early 1945 reflected the cumulative impact of combat experience, improved equipment availability, and familiarity with specialized ammunition, including HVAP. Crews that landed in Normandy in June 1944 often felt genuinely apprehensive about facing German armor, particularly Panthers and Tigers. By early 1945, after months of sustained combat, significant training improvements, increased availability of 76mm Shermans, and growing familiarity with HVAP ammunition, American tankers approached engagements far more confidently. This psychological shift had direct tactical consequences. Confident crews fought more aggressively, took calculated risks when opportunities appeared, and exploited tactical advantages. While HVAP ammunition alone did not create this transformation, its availability and proven effectiveness contributed meaningfully to improved American armored force morale and tactical performance. The legacy of HVAP development continues influencing modern ammunition design. American armor doctrine from 1945 onward consistently emphasized ammunition effectiveness as a critical component of tank design. Modern tank ammunition uses depleted uranium or tungsten alloy penetrators, materials chosen for essentially the same density and hardness properties that made tungsten carbide effective. In World War II, the underlying principle remains constant: concentrate maximum kinetic energy into a small, extremely dense projectile, moving at the highest achievable velocity. The continuity from 1944 HVAP to present-day armor, piercing fin, stabilized, discarding sabot ammunition, illustrates how foundational lessons from World War II continue directly influencing military technology. Soviet and later Russian tank ammunition development followed remarkably similar paths, independently recognizing that armor-piercing capability depends heavily on projectile material properties and kinetic energy delivery. The global tank ammunition industry had its technological roots in the HVAP experience, where engineers first demonstrated conclusively that specialized ammunition could partially overcome armor protection advantages. September 19, 1944, when Sherman crews first engaged Panthers with HVAP ammunition at Aracourt, marked a genuine turning point in the psychological balance of armored warfare. German crews who had fought confidently behind their armor learned that American tanks could pose a serious frontal threat. American crews who had felt outmatched gained meaningful confidence from knowing they possessed ammunition that could defeat Panthers under favorable circumstances. This shift in tactical psychology, enabled by tungsten core ammunition produced in American factories, influenced every subsequent armored engagement of the European War. HVAP ammunition, though never available in desired quantities, provided enough improved capability to transform American tank crews from uncertain defenders into confident attackers willing to engage German armor directly. The story that began with War Daddy II sitting in Kummersdorf Proving Ground, being meticulously tested by German engineers who correctly identified the 75mm Sherman's limitations, ended with those same engineers facing a weapon they had never anticipated. Not a completely new tank design, but an evolutionary improvement to the existing platform, a more powerful gun, more effective ammunition, the same reliable automotive excellence they had documented and grudgingly admired. Now, armed with teeth sharp enough to hurt Panthers, the crews who fired those first HVAP rounds in combat, watching tungsten cores punch through armor that had seemed invincible, demonstrated that industrial capacity and material science applied intelligently to urgent tactical problems could overcome seemingly insurmountable technical disadvantages. German engineers at Kummersdorf had tested what Americans had already built. They could not anticipate what American industry was capable of building next. This fundamental blindness to American industrial dynamism and continuous improvement philosophy characterized German intelligence failures throughout the war. They saw snapshots of capability at specific moments, but failed to understand the underlying systems that generated constant evolution. By the time German analysts compiled their reports on the 75mm Sherman's inadequacies, American factories were already producing the 76mm version. By the time German intelligence identified the 76mm as a threat, American ordinance had developed HVAP to enhance its capabilities. This cycle of improvement, driven by combat feedback and enabled by industrial depth, proved more valuable than any single technical advantage. The lesson learned at considerable cost on battlefields across Europe remains directly relevant for military planners facing technological challenges of modern warfare. Superior individual weapons matter, but adaptive industrial systems matter more. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.